Hello everybody. We continue on our discussion of lower and upper sums. In this video we're going to look at just one theorem, a little theorem that's going to explain the relationship between lower and upper sums for one partition or even between lower and upper sums of multiple partitions. So let's get to it. So we're going to start as we usually do with, let's see, we'll tell you it's a theorem here. And the theorem is going to start with our usual setup. We have a function on a closed interval a, b to the reals, and it's going to be a bounded function. This unlocks the axiom of completeness. We get suprema and infima as much as we want. Then we're also going to have a couple of partitions. So these will be partitions of the interval a, b. So first thing is that if this W partition is a refinement of X, okay, meaning every term in W was already a term in X. Okay, so if W is a refinement of X, then, so here's what I claim is going to happen. If I look at the lower sum for F of this partition X, then this is going to be less than or equal to the lower sum for the partition W. Furthermore, the lower sum for the partition W will be less than or equal to the upper sum for the partition W. And the upper sum of W is going to be less than or equal to the upper sum of X. Okay, so what this is telling you is that when you refine a partition, the lower sums will get bigger and the upper sums will get smaller. Okay, X gets refined, the lower sum goes bigger. X gets refined, the upper sum gets smaller. All right. The second thing we're going to prove is that this is no longer going to have the assumption that W is a refinement. So just in general, we have that the lower sum of W is less than or equal to the upper sum of X. All right, so if you like, every lower sum will be less than or equal to every upper sum. Okay, so let's just write it. Every lower sum for F, okay, this is for this particular F, is less than or equal to every upper sum for F. So that's a pretty handy thing, right? I have a lower sum over to the left, I have an upper sum to the right. A, I know the upper sum is bigger than the lower sum no matter what partitions we're talking about. All right, so let's get to the proof. So one part of the proof is going to be pretty easy, right? So we're looking at 1 here. And I claim this inequality, this blue one, is going to be very simple. So what will make it simple is us just writing down the definitions. Okay, so let's recall. So we're going to recall. What would be, say, the lower sum for W? So I know this is going to be some sort of sum. And we'll say we can go K goes from, I don't know, how about 1 to N? And we're going to be taking the infimum of F applied to all of the intervals that make up W. So maybe I'll call these intervals for here J for right now. Okay, and then I'll multiply by the length of each J. Okay, and then the upper sum for W looks almost identical, only I have a supremum. That's it. That's the only change between them. And if you have a particular set and you take the infimum of that set and you also take the supremum, it is always the case, right, that the infimum, which is the greatest lower bound of the set, is always less than or equal to the least upper bound of the set. And so from here, we immediately conclude that the lower sum for W is less than or equal to the upper sum for W. All right, so this bit, no problem. Okay, fine. So what's the hard part? Well, the hard part is these inequalities on the end. All right, fine. So what we're going to do, and this is rather kind of clever, is we're going to prove these inequalities, and we'll just stick to say the lower one, but the upper is almost identical. We will prove it using induction. All right. So remember, in this case, W is a refinement of X, meaning you start with X and then you add more points. So W has more points. So for example, we might know that X is an M partition and W is an N partition. So N here then would be at least as big as M. And we just want to know how far apart they are, and that's what we'll do the induction on. Okay, so we're going to do induction on N minus M. So our first base case, we'll actually have two base cases here. So this is base case 1, is when N minus M is equal to 0. So in this case, this is equivalent to saying N and M are equal. But if N and M are equal, that means I refined an M partition and got an M partition. That means I didn't add any points. So that would just tell me that X and W are the same. And that, of course, certainly implies that the lower sum for X and the lower sum for W are the same, because they're the same partition. All right, so that's an easy base case. All right, here's a second base case where N and M differ by 1. So in this case, N is equal to M plus 1. So in this case, let's write down then our X. X would be X0, X1 through Xm. And so then our W is obtained by adding one extra point. And I don't know where it goes, so I'm just going to say, well, let's say it's going to occur after the L minus 1 position, and we'll call that extra point Z. So it'll go between XL minus 1 and XL, and we get all the way now up to XM. Okay, so W has one extra partition. Okay, so first, let's write down our LF of X. So this is going to be a sum. K goes from 1 to M. We take the infimum, F of, all right, I'll use our notation here, I sub K, for the interval from xk minus 1 to xk. So this will be F of ik, and I multiply by the length of ik. All right, so that's it. That's what LF of X looks like. Now remember the goal. Our goal is to show that when we take the lower sum for a refinement, it's going to get bigger. All right, so let's write down the lower sum for the refinement. Okay, well, I can start the same way. I have this sum. I go from 1 to, well, when I get up to Z, something funky happens in terms of our indexing. So it's probably good to split this sum up. So let me go all the way up to L minus 1. Then I have the infimum of, well, they're the exact same intervals. So I have F of ik, and then the length of ik. So up until I get to L minus 1, I actually get the same thing. In fact, let's break this up. All right, I can go up to L minus 1, and then I have the infimum of F of ik times the length of ik. And these match so far. So in terms of being greater than or equal to, we're good so far. And of course, there's more going to happen here, right? What's the more? The more is, well, now I have to go the rest of the way from L to M. Okay, well, let's see what we have for W. When I get up to L minus 1, the next term isn't something coming from the X, right, partition, right? Now I have this interval from X L minus 1 to Z. And I might as well just give it a name. Well, how about XL minus 1 to Z? Yeah. So the next piece I have is going to be the infimum of f applied to the interval xl minus 1 to z times the length of the interval xl minus 1 to z. Okay, that gives me this piece. All right, well, then I get this next piece. So plus the infimum of f applied to the interval from z to xl, and then multiplied by the length of the interval from z to xl. Okay, so that takes us up to here, and now we just jump back on the train. We're going to go from L to L plus 1, etc. That's actually going to look just like we would have before. We'll start from L, and we go to M now, and we're going to have the infimum. Or sorry, this should be L plus 1, right? We go to the following one. We do the infimum now, and it's back to our I sub k's again, times the length of I sub k. Okay. Okay, so this doesn't quite match up with this bottom piece because it starts at L plus 1. So we start here, we had going from L to M, now we have all this bit. So in fact, what we could do is even break this up further, right? We could have said, okay, let's start this at L plus 1, and then you just have this one term in the middle, right? So I could start here at L plus 1 and now have a plus, and what happens in between? I'd have one term, the infimum f of I sub L times the length of I sub L. And if I do that, you can see the yellow stuff matches, the blue stuff matches, and so the only difference are these two pieces for the W and this one piece for the X. And so that's what we need to compare. And if I can show that the stuff for the W is at least as big as this one little piece for the X, then we've finished this part of the proof. All right, so let's see. What if we take this one little piece for the X? So I have the infimum of f of I sub L times the length of I sub L. And this is equal to, well, let me take what is this length of I sub, I said K here, that should be an L. What is the length of I sub L? This is equal to, I take X sub L, and I subtract X sub L minus 1. Okay, but let's look at this little piece up here, right? This XL minus XL minus 1, I could get that in another way. I could get it by doing XL minus Z plus Z minus XL minus 1. And so I could break now this infimum up as the infimum, or this product really, the infimum of f I sub L times, and I'll just copy it here, XL minus Z plus the infimum f of I sub L times Z minus XL minus 1. Okay, is this good? Well, yeah, actually it is kind of good because this XL minus Z, right? This matches up with that piece right there. And this Z minus XL minus 1, that matches up with this piece right here. And so now all I have to do is compare the infimum of F on this set with the infimum of F on I sub L. Now let's just quickly sketch this out. I have XL minus 1, I have XL, and somewhere in the middle I have Z. And what is I sub L? That's this entire interval. If I take the infimum of F on XL minus 1 to Z, that means I'm just looking at this piece right here. Okay, so that's what that is. If I take the infimum, so the greatest lower bound of f just on this piece, then I should have fewer opportunities to get smaller than if I take the infimum on the entire interval IL. Right? There's more opportunities to get smaller when you have more in your domain. And so what that tells me is that the infimum for f of I sub L should be less than or equal to the infimum for f of this green bit. And so I'm allowed here now to replace then the infimum by the infimum on this smaller interval. And then I can just copy the xl minus z, or I can turn it into, if you like, the length of xl minus 1, or rather of z to xl. Okay, and the same thing happens in the second component. Again, if I take the infimum over the entire interval, that will be less than or equal to what would happen if I took the infimum over just part of the interval. So this will be less than or equal to the infimum, again, of f, but now it'll be from, I've mixed these up, haven't I? This should be, yeah, I swapped these. This is xl minus 1 to z, and then this is from z to xl, okay, times the length of the interval from z to xl. Okay, and this is it, because we have now shown that the piece from x, right, that the only piece from x that's different from the pieces of w is less than or equal to the sum of those two pieces, right, from w that were distinct. And so from this, we conclude that LF of x is less than or equal to LF of w. Okay, so this is the base case, right? That feels pretty bad, right? Like all we've done is base cases, but that's actually all we need to do. And the reason why is because if I have any other refinement, right? Say it's got 5, I can do it one piece at a time, right? Because our partitions are all finite. Okay? So since partitions are finite, we can always refine x to get w by adding one point at a time. Right? And because everything's finite, right, we will terminate the process. So if m and n were 8 apart, I would add 1 point, and this base case would now tell me that the lower sum gets bigger. Now I add another point, and again, the base case tells me the lower sum gets bigger. And I just keep doing that 8 different times, and on the 8th time, I go, oh, look, and the lower sum got bigger again. And that's it. Okay, so by induction, the proof of 1 is complete. Okay, well, I didn't say anything about the u's, okay? But I'll just say the case for UF is similar. Okay, and there the whole idea will be that when I go to take the supremum over a larger interval, it can only get smaller, okay, instead of bigger. Okay, so that proves the first statement. So the second statement is a more general one. Now I have a W and an X, and I don't know that they're refinements of each other, right? I just have two random partitions, W and X, and I want to know that the lower sum for W is bounded by the upper sum for X. Okay, so it's going to turn out we can use part 1 to prove part 2. Okay. All right, so I have w, I have x, but once I have w and x, then I have, so let's say there's w, and then I have an x, but then I get their common refinement, w wedge x. And so I have this refinement, and so by part 1, here's what we know. If I take the lower sum for w, this is going to be less than or equal to the lower sum for any refinement of w. Okay, well, there's a refinement, w wedge x. Okay, but we also know by part 1 that if I take any lower sum, it is going to be less than or equal to any upper sum of the same partition. So I can replace lower here with upper, and I still have this refinement. But now, again, using part 1, I know that if I take a refinement, so in this case, a refinement of x, the upper sum will get smaller. So I had the upper sum for x, I take a refinement, the upper sum is smaller. And so what have we concluded? We've concluded that the lower sum for w is bounded by the upper sum for x. That's just a really cool way to finish it off. Okay, so that's what we're going to need in order for us to proceed further. So in the next video, we're going to define our first integral, although they're only sort of part way to being integrals. They're going to be called upper and lower integrals. All right, we'll see you next time.